You see, last lecture we were looking at the notion of dimension, okay, and we noticed that there is a notion of dimension from the topological point of view, that is the the definition of dimension of a topological space, and then there is also the notion of Krull dimension of a ring, okay, and somehow these two are related in the sense that the dimension of a for example, the dimension of affine n space, the topological dimension of affine n space is the same as the Krull dimension of the ring of functions on affine n space, okay. So let me recall again to refresh your memory and also so that you feel a little comfortable about things. Let me recall what was going on. So see, on the, so we have as usual the geometric side, and we have on this side the commutative algebraic side, and here if you take affine space over K, affine n space over K, this is just Kn, K cross Kn times given the Zariski topology, where of course K is an algebraically closed field, okay. As usual, you can always think of it as complex numbers if you want to be very concrete. So in that case this will be just Cn, n copies of C given the Zariski topology, and then the ring of functions. So the association that I am interested in is called is given by the symbol A of a variety or an algebraic set, okay, and it's defined only for varieties properly. This is, well, this should be thought of as giving you the ring of functions. So you have the space here, and here you have its ring of functions. So on this side you have the space, and on this side you have rings of functions, okay. So if you take affine space, of course what kind of functions? Functions are of course polynomial functions. We are only interested in algebraic functions, polynomial functions. So if you take this is going to be this is k x1 etc, okay, and the fact is that you see what I want to say is that there is also an association that goes from this side to this side, okay, which makes this again a bijective correspondence, okay. So again, you know, this is another instance of you know, the interaction between algebraic geometry and commutative algebra, that there is always a dictionary which goes from the geometric side to the commutative algebraic side and goes back and forth. So see, initially, you know, we had such a dictionary where we had taken on this side, for example, we have seen it in other contexts. For example, on this side, if you took, you know, closed subsets, that is algebraic subsets, then what you can get on this side as a bijective correspondence are the radical ideals, okay. And if you, and under this correspondence, the irreducible algebraic subsets, the irreducible closed subsets, they will correspond to prime ideals, okay, which are of course radical. And the, of course, the points, the singleton sets consisting of points, they will correspond to the largest ideals, which are the maximal ideals, largest proper ideals. So that is one correspondence we have already seen, and in that correspondence, what goes from this side to that side is, given a set here, you associate the ideal of that subset, okay, and what goes from there to here as the inverse map is, given a an ideal, you look at the zero set of the ideal, okay, and that gave a bijective you know, correspondence. Now rather than going from algebraic sets or varieties to ideals, what you do is you go from algebraic sets or varieties on this side to rings of functions, okay. So that is the change in the point of view, but the fact is that again you get a nice bijective correspondence. And so let me explain. See, what is happening is, see, if you, why this is so important is because if I take dimension topological of an, this is of course n, okay, and that is just a translation of the fact that the dimension, the Krull dimension of this polynomial ring is n. So the topological dimension of a space here, of course when I say space here, actually what I am meaning is a variety here, okay. A variety means an irreducible closed subset of an. In particular, an itself is an irreducible closed subset of itself, okay. So this is the biggest possible variety in an, and if you take any variety here, then you can associate to it its ring of functions, okay, and the dimension of the variety will be the same as the Krull dimension of its ring of functions, okay. So what I want you to understand is that if I take X variety, affine variety, okay, then you know X is of the form Z of some prime ideal, okay, because you know if a variety, I mean if an algebraic subset is always given as zero set of an ideal, and if that algebraic subset is irreducible if and only if the radical of the given ideal is prime. So in particular, and of course taking the zero set of an ideal and the zero set of its radical does not create any changes. The zero set of an ideal is the same as the zero set of its radical. So any irreducible closed subset of affine space is always given by the zero set of a prime ideal, okay, and of course you know this prime ideal is unique. It's unique under that bijective correspondence between irreducible closed subvarieties, I mean irreducible closed subsets in an and prime ideals of the polynomial ring. So the fact is, if you take a affine variety like this, then what is it that you are going to get on this side? What is it that you are going to get on this side? You are going to get the space of the ring of functions, algebraic functions on X, okay, and the ring of algebraic functions on X will be X is of course Z of P, and in fact it is actually A of An by P. It is just this is just K x1 etc xn by P. This is what it is, and so let me draw a line like this, because this statement was for An. Now I am making a statement for any affine variety closed inside An, okay. Then for any variety the ring of functions is defined like this, and then you again see that the dimension, the topological dimension of the variety, these two are equal. Here also the dimension, the topological dimension of the variety will be the same as the Krull dimension of its ring of functions. This will happen. So I want that, so this is a generalization of this. This is a generalization of this statement, which is true for all affine space, and I also want to tell you what is this arrow that's coming in the other direction, okay. That arrow is actually max spec. That is the arrow that's going in this direction. So let me explain that. So let me explain, let's keep this diagram as the basic diagram that we want to understand, and let me expand upon this, okay. So the first thing that I want to explain is, well, just to recall, how did you get the topological dimension is equal to the Krull dimension, the topological dimension of An to be equal to the Krull dimension of the polynomial ring? That's because the topological dimension is supposed to be the, you take chains of strictly increasing chains of irreducible closed subsets, okay, and then you take the largest possible such chain and subtract 1 from that. That is the topological dimension, if at all it is finite, okay. You have to take large, if it is not finite then the largest possible will be infinite and then it will become infinite dimension, okay. So how does one define the dimension of a topological space? You simply write out and you try to look at existence of a chain of irreducible closed subsets, okay, irreducible closed subsets which are contained, each one contained in the next. Try to look at such a chain and try to look at the chain being strict, namely that there are no repetitions in successive members of the chain, and among such chains try to take the maximal length ones, namely the ones with as many terms as possible, and you, if this maximum is a finite number, okay, you take away 1 from that, that will be the topological dimension, okay. Now why does that translate to this side, into this side, to give the Krull dimension? That's because any closed subset here corresponds to a radical ideal, any irreducible closed subset here corresponds to a prime ideal, and if you give me a strictly increasing chain of irreducible closed subsets, that will correspond to a strictly decreasing chain of prime ideals, okay. So what will happen is that the fact is that the largest, largest in the sense, the chain, a strictly increasing chain of prime ideals of maximal possible length, okay, is n plus 1, okay. And of course the easiest thing is you take 0, start with the 0 ideal, then take the ideal generated by one variable x1, then that is contained in the ideal generated by x1 and x2, and then at the ith stage is generated by x1 x2 etc up to xi, and you go on up to n. This is a strictly increasing chain of prime ideals, its length is n plus 1, and therefore the Krull dimension becomes n. So the Krull dimension of a commutative ring is defined to be the supremum of the heights of the prime ideals, okay. And what is the height of a prime ideal? The height of a prime ideal is the maximum possible length of the maximal possible chain that you can, descending chain, strictly descending chain of primes that you can get starting from that prime ideal, and then you have to take away one from that, okay. That is the reason in all these definitions you will see that instead of taking a chain from Z1 to Zm and taking the supremum and calling this and taking the dimension to be 1 less than that, we rather start with 0, we start with the index 0, okay. That is the reason you start with 0, okay. Anyway, so the fact is, and why is the crude dimension of this equal to n? Because whenever you have a finitely generated, whenever you have an algebra, namely you have a quotient of the polynomial ring which is an integral domain, then the crude dimension of that is actually the transcendence degree over K of its quotient field, and the quotient field of this is simply the field of rational functions in n variables, okay. It just consists of ratios of polynomials in n variables with the denominator polynomial not equal to 0, and that has transcendence degree n. It has, so transcendence degree is analogous, is for algebraic independence the analog of dimension for linear independence. Just like for linear independence, dimension is cardinality of a maximal linearly independent subset. For algebraic independence, transcendence is the cardinality of a maximal algebraically independent subset, okay. So it is analogous to what happens in linear algebra. So transcendence degree measures the largest, it gives you the number of maximum, I mean the maximal number of transcendental elements which are algebraically independent from one another, okay. That is what it gives. So just like dimension of vector space gives you the maximal number of linearly independent elements, okay, linearly independent vectors. So and the transcendence degree of this, the quotient field of this is n, which is very clear intuitively, but you need to prove it, okay, using some something from you have to use some field theory to prove it, okay. And now you see, so the first thing that I want to explain is why do we define the ring of functions on X like this, okay. Why do we define the ring of functions on X to be the ring of functions on the whole space divided by the ideal of X. So in fact this is, I can simply write it as a of an of K divided by I of X. I of X is P, where script I is the ideal of the given subset, okay. So I of X is P, right. So here also I can write that P is equal to I of X, okay. And so in a way, you know, previously we were associating to X I of X, which is the prime ideal. Now what you are doing is you are not associating X to the prime ideal, but you are associating it to the quotient by that prime ideal. Instead of looking at the ideals on this side, you are looking at quotients by those ideals. That is the only difference. But the advantage of looking at quotients by those ideals is the fact that you get rings of functions. And why is that? That's what I am trying to explain. It's very easy. See, what you do is, you see, you look at a of X. So this is you define it to be functions from so functions from X to K which are given by polynomials, by restriction, by polynomials. So look at this definition. So a of X are just functions, they are maps from X to K, and the point is that this map it should be an algebraic function, okay, which means it should be a polynomial, okay, and of course what polynomial in n variables, because x is a subset of an and any polynomial in n variables is a function on an. You can evaluate it at each point of an, okay. So actually what is happening is when you go from here to here there is something that is already happening. So if you apply this condition, you see if you apply this definition, so if I write a of an, this will be functions from an to k which are given by polynomials. And you see if I take the ring of all polynomial functions in n variables, then I have a map like this. That map is you start with a polynomial in n variables and you use that f to define a function. Think of f is here now a polynomial, define that as a use that f to define a function. Let me if I want to be very strict, to distinguish the fact that here I am thinking of f as a polynomial and there instead of the polynomial I am looking at the function that it defines. What I will do is I will put evf. This is evaluation of f. Evaluation of f from an to k is a function. This is what f goes to. What does this do? Give me any point in an, you simply evaluate that point f at that point, you evaluate the polynomial at that point. This is the map. So you are just associating f to evaluation of f, okay. And what you must understand is, you see if you take functions like this which are given by polynomials, then it is very clear that if you take two such functions, their sum is also given by corresponding sums of polynomials, right. So if a function is given by a polynomial, then a sum of two such functions is also given by sum of the corresponding polynomials. Product of the two functions will be a function that is given by product of the corresponding polynomials, and of course there are constant functions here which correspond to the constant polynomials. In other words, what I am saying is that this map is actually a ring homomorphism. I am saying this is a ring homomorphism. This fellow on this side is actually a ring. That is what you must understand. Take it here also. If you, when I say functions which are given by polynomials, if I have two functions which are given by polynomials, then their sum is given by the sum of polynomials, okay, and the product is given by product of polynomials. So these are all rings, okay, they are commutative rings and they contain constants. The constant functions are always there because constant functions come from evaluation of constant polynomials. So constant functions are there. So these are k algebras. A k algebra is nothing but a ring, a commutative ring with k which is also a vector space over k, okay, and in such a way that the multiplication in the ring is compatible with the scalar multiplication. Lambda times fg is the same as f into lambda times g, okay. So the vector space structure and the ring structure, they are compatible. That is what an algebra is, okay. So these two are both k algebras, okay. So they are rings, and the fact is here also I can start with, take a polynomial in n variables, I can have this map. What is this map? This is just f going to evaluation of f restricted to x, from x to k. It is the same map, but you restrict it to the subset x after all, because x is a subset of an, you can always restrict the map. That is what I mean to say that these are functions which are given by polynomials. When you say they are functions given by polynomials, they are actually given by restrictions of polynomials. That is what this map is. okay. And what you must again understand in this case also is that this is a ring homomorphism. It's also a ring homomorphism because f plus g, evaluation of f plus g will be evaluation of f plus evaluation of g, evaluation of f into g will be evaluation of f into evaluation of g, and evaluation of lambda will be just lambda if lambda is a constant polynomial, alright. So you can see that this is not just a ring homomorphism, it also preserves the vector space structure. Mind you, what is there on the left side is also a K algebra. This is a commutative ring with 1 which is also vector space over K, and the scalar multiplication is compatible with the ring multiplication. If you take a scalar lambda and if you take two ring elements, two polynomials f and g, then lambda times fg is the same as lambda f times g, that is the same as f times lambda g. It really does not matter to which factor of a product you multiply a constant, you are going to get the same polynomial, right, in a product of polynomials. So these are actually K algebras. So what is happening is that you are getting ring homomorphisms which are actually homomorphisms of K algebras. These homomorphisms also satisfy they are linear, they also respect the vector space structure. So evaluation of f plus g is evaluation of f plus evaluation of g. This respects addition, it respects multiplication, and it respects scalar multiplication, okay, and evaluation of lambda is lambda. All this is true, and this is for f g in the polynomial ring and every lambda in the every constant polynomial, okay. So this is so in fact instead of writing ring homomorphism, let me write K algebra ring homomorphism. K algebra means it is a ring homomorphism which is also a K vector space map, and of course the algebra condition is on the rings, that the scalar multiplication and the ring multiplication are compatible, that is, you also have lambda times fg is equal to lambda f times g is f times lambda g. This is the algebra condition, that multiplication by a scalar is well behaved with respect to multiplication between two ring elements thought of as vectors, okay, fine. So now what I want you to understand is that this map is an isomorphism. This map is actually an isomorphism because you see, if first of all if you have two polynomials, it is a ring homomorphism. To show that it is an isomorphism, I have to show it's surjective, I have to show it's injective. To show it's injective, I have to show its kernel is 0 if you want, because it's a ring homomorphism. It's surjective by definition, because my definition of ring of functions is that they are given by polynomials, so it's automatically surjective. Both of these maps are surjective because by definition a function is supposed to be coming from a polynomial, so both maps are surjective, mind you. The only thing that you will have to worry about is injectivity, okay. So if a function f is such that evaluation of f is 0, okay, for every point of an, then that function has to be the 0 polynomial. That's that's because if it's not the 0 polynomial, okay, then you should be able to find some point where if you evaluate it you will get a non-zero element of K, okay. So that tells you that this is injective, and it's already surjective, so it's an isomorphism, and this is what tells you that this definition is correct, that to think of the ring of functions on an as the polynomial ring is correct because of this argument. Now in the same way, if you look at this argument, what you will get is you will get this actually. Okay, what will happen is that this ring homomorphism is surjective. What is the kernel of this ring homomorphism? This ring homomorphism is not injective, it has a kernel. What is a kernel? It's all those functions whose evaluations when restricted to x become 0, but that's precisely all those functions which vanish on x. But what are the functions which vanish on x? They are precisely the functions in this they are precisely the polynomials in the ideal of x. Therefore the kernel of this map is actually ix and is surjective. Therefore source modulo the kernel is isomorphic to the target. So you get that k x1 etc xn modulo ix is isomorphic to ax by this map. Okay, so these two statements justify that these definitions are correct. Okay, so they give you the naturalness, you know, behind these two definitions. Okay, so let me write that down. Let me write here kernel of evaluation is 0. This is so, you know, this ring homomorphism is just EV because it's f going to EV of f, and this ring homomorphism is EV restricted to x. You evaluate and then restrict it to x, or you do the evaluation on x. So kernel of evaluation is 0, kernel of evaluation restricted to x is ix, and so it tells you so this tells you that a of an is isomorphic to k x1 etc xn, and a of x is isomorphic to k x1 etc xn modulo ideal of x. Okay, so what you are doing is that, see here, by brute force we write like this, that is we really think of the functions as think of the polynomials as functions. Okay, but if you want to be more strict you should do it like this. This is a stricter way to do it. Okay, so in which you distinguish between the polynomial and the function that it defines by evaluation. Okay, so when you make this distinction you get these isomorphisms, not equalities, you get isomorphisms in a very nice way. And why is that nice? Because this can also be written, mind you, this is also equal to k of x1 etc xn modulo ideal of an, because ideal of an is 0, right. So what it tells you is that this formula ax is k x1 etc xn by ix works even for x equal to an. Okay, so the so now you get this you get this kind of you get a philosophy that if x is embedded in as an irreducible closed subset of a bigger space, okay, this is irreducible closed in a bigger space, then a of x has to be a of y divided by the ideal of x in y in a of y. You get something like this. Okay, so so what this tells you is that it tells you that you know the notion of, so the point that you must appreciate here is that this quotient ring homomorphism, this is a quotient homomorphism because it's surjective. Surjective homomorphism is always a quotient, okay, because the target is a quotient of the source by the kernel, so it's a quotient, and the quotient is actually thought of as restriction of functions. Okay, so the moral of the story is that whenever you see a quotient in commutative algebra, algebraic geometrically it means that you are restricting functions to a subset, closed subset, okay. That is the geometric meaning of what a quotient is, that is what this is, okay. So the quotient homomorphism is just gotten by restricting functions literally, right. So that tells you why, you know, it is correct to define the ring of functions for an affine variety like this, okay. Of course we will really not worry about all the time writing isomorphic to, okay. So by abuse of notation we will simply put equal to, okay, but what that equality is, to be very precise, it is an isomorphism, because when you simply write the ring they are actually polynomials, but if you want to think of them as functions you must evaluate those polynomials. So there is a difference, and this isomorphism is to signify that difference, but then one forgets this and by abuse of notation keeps writing equal to, okay, fine. So this much is clear. Then I want to explain why this and this are one and the same. Why are this and this one and the same? See, that's quite that's again quite clear, because if you look at the way it goes, you see what is, see if you take x, okay, and you in x if you give me a sequence of irreducible closed subsets, okay, so these are all irreducible closed in x, okay, then you see what these will correspond to is, see mind you x is sitting inside, x itself is an irreducible closed inside an, x itself is an irreducible closed inside an, okay. So if you go to the polynomial ring, the ring of functions on an, which is k x1 etc xn, okay, then you see this x as a closed subset of an on this side will correspond to the ideal of x, which is prime, okay. Mind you that there is an inclusion like this, okay, because all these are all closed in x, and that is further closed, irreducible closed in an, okay. So what will happen is you will get something like this, you will get ideal of Zm which way, so it should go the other way, so ideal of Z0 will contain, so it will be like this, ideal of, so let me write it, proper containment ideal of Zm minus 1 and so on, proper containment ideal of Z0. So this diagram on this side translates to this diagram on the other side, okay, and of course you know why this is, because we have a on this side to that side, if you apply this I, you know that's a bijection, because its inverse is given by Z, you know this bijection, okay. This is a bijection between radical ideals and closed subsets, and if you are only looking at irreducible closed subsets, then it's a bijection between irreducible closed subsets and prime ideals, okay, and of course its inclusion reversing, alright. So see what this will tell you is that in the earlier lecture I defined what is meant by height of a prime ideal. What is the height of a prime ideal? You start from that prime ideal and then you take a descending sequence of strictly descending sequence of prime ideals, okay, and take the maximal possible length, that is the height of the prime ideal, okay. So you know if I start with Ix and if I take a strictly descending sequence of prime ideals starting from Ix and going down all the way to the smallest prime ideal, which is 0. Mind you, 0 is a prime ideal, therefore because these are all integral domains, 0 is a prime ideal, polynomial ring is an integral domain. So then what this will tell you is that the height of that plus this m, okay, and if I take the, see here, if I take m to be maximum, if I take the maximum such m, I am going to get dimension of x, okay. Dimension of x is actually supremum of all such m, okay. And suppose as in this case, if what this will tell you is that if the dimension of x is say if the dimension of x is say r, okay, then you have a maximal chain here which is length r, okay, that will correspond to, that will tell you that this has length r, okay, I mean this will be r, okay, plus you know if I further continue, because of maximality, this will be if I further continue it to go all the way down to 0, which will give me the height, then if I add both I should get the dimension of the polynomial ring, okay. If I take this, okay, with m equal to r, which is the maximal possible, and then if I further go down, okay, from I of x to 0, that part will give me the height, that plus this r will give me the dimension of the polynomial ring. This is just reflection of this fact that you know height of a prime ideal plus dimension, Krull dimension of r mod p is equal to Krull dimension of r, okay. I wrote down a formula like this last time, that is if r is an integral domain which is finitely generated as a K algebra, then and p is a prime ideal of r, then the height of the prime ideal plus the Krull dimension of the quotient is equal to the Krull dimension of the whole ring. That is just a reflection of this fact that I explained just now. So moral of the story is that the dimension of x will be actually, if the dimension of x is r, then the height of Ix will be n minus r. So the dimension of x is r here, this will correspond to height of Ix is equal to n minus r, because r plus n minus r adds up to n, which is the dimension, the Krull dimension of the whole polynomial ring. So the moral of the story is the but then what is n minus r? N minus r is the dimension of the quotient, but what is the quotient? The quotient is the ring of functions. That is why the dimension of the topological dimension of x here corresponds to the Krull dimension of the ring of functions, okay. That explains why these two are equal, okay. Do you understand that? So I'm just trying to give an explanation why these two are one and the same, right. So I'll stop here and then we'll continue the next talk.